In this video, I want to offer another specific example of an SN2 type reaction, but in this case, it's going to be on a secondary substrate. And what that allows me to illustrate is the fact that SN2 reactions proceed by inversion of stereochemistry. So what we have here is 2-bromobutane, and in particular, this is the R stereoisomer of this particular molecule. And what we're going to end up doing, of course, is displacing that with a nearby nucleophile. And in this case, the nucleophile is an S-. This is a reasonably strong nucleophile and not particularly basic. If you see a sodium associated, almost always in organic chemistry, that is just sodium plus, and it is serving as a spectator. So the interesting thing here, the nucleophile part, is the S-. And what's going to happen is the highest occupied molecular orbital, which is a lone pair on the sulfur, is going to go ahead and attack, and it's attacking the lowest unoccupied molecular orbital, which is of course the CBr sigma star. And I'm only drawing the empty lobe that gets attacked, but of course you know that there are other lobes there, and I'm just going to leave them empty so as not to confuse the issue more. But specifically, the highest occupied molecular orbital is the lone pair of the sulfur, and the CBr sigma star is the lowest unoccupied molecular orbital. Since what you're doing is filling the antibonding orbital of the carbon-bromine bond, that means that the carbon-bromine bond is going to break, and that causes this pair of electrons that was in the carbon-bromine bond to become a bromine lone pair. And so we've already discussed previously that what's going to happen is you end up displacing the bromide, you end up substituting for the bromide, and so now you're going to have the Br- just floating around nearby in space, and naturally the sodium is just floating around as a spectator as well. Nothing has changed there. And so the only thing that's interesting is what happens to the carbon-containing substrate. And since you attack the sigma star orbital, you attack from the backside of the carbon-bromine bond, and so it shouldn't surprise you to learn that what happens is you end up inverting that stereochemistry. And so now the sulfur ends up bound there on the backside of where the bromine was. So it came in from the back. What I'm going to illustrate down here is a reaction coordinate diagram for this entire process. And basically, we had the substrate with the leaving group on it, as well as the nucleophile floating around in space. And they had some energy. And eventually, they go through this reaction, and all those two steps happen at the same time. And that ends up leading down to the new products, which of course are now the nucleophile is bound to the R group, and that's all we really care about, and what's left over is just the leaving group floating around by itself, or in this case the bromine. But the reason why I'm illustrating this on the reaction coordinate diagram is to say that there's particularly one interesting point that we want to look at, and that is the transition state of this process. So in other words, as you go through from the nucleophile and the reactant sitting by themselves and end up at the product and the leftover pieces, the detritus, the leaving group minus and the sodium plus sitting by themselves, there's one interesting place in the entire reaction, and that's what happens as this set of arrows is taking place, as this mechanism is happening, as the sulfur is coming in, and as the bromine is leaving simultaneously. So I've drawn these brackets and listed that as the transition state, and I'm now going to go ahead and build what that transition state looks like, and that will illustrate why you end up with that specific stereochemistry. So here what I want to illustrate so far is that all I've done is taken this molecule right here and rotated it this way, and then flattened the bromine bond. So I rotated it and then pushed the bromine back into the plane. And the other thing I've done is I've drawn out the actual LUMO, which is to say the carbon-bromine sigma star. And that's to show where specifically this orbital is. So what we have is a large empty lobe right there, a small lobe of the other phase, a node, a place where the electrons are not allowed to be, another lobe, smaller on the bromine, and then an empty lobe out there. But the thing to keep in mind is that the carbon itself is, at the moment, delta plus. And the reason why the carbon is delta plus is because the bromine is delta minus. And so the sulfur is attracted to the plus side. It's attracted to the carbon itself, and specifically, it's attracted to the backside of this orbital. And so this is what's going to happen. You're going to fill that orbital, and as you fill that orbital, then eventually this bond is going to break and end up on the bromine. But I wanted you to see how the carbon chain was oriented before I drew it fully in the transition state realm. So the key thing about the transition state itself is that the carbon chain for the transition state is going to be perfectly flat. The methyl is going toward the camera, and H is behind. And meanwhile, this right here is the ethyl chain. And so what we have is now an empty orbital on the carbon that's left over. This is essentially a large empty p orbital that's just sitting here at the moment. And what's happening on the one side is that the bromine is leaving but hasn't yet fully left. And so its electrons haven't fully broken and become a lone pair, but it's on its way there. And the reason why that's happening is because the electrons from the sulfur are coming in, but they haven't fully arrived yet. So the key part of the transition state is that you are in this sort of nether region where at the moment there are kind of 5 bonds to the carbon, but kind of 3 bonds. So the real way to think about it is that you have 3 full bonds to this carbon that aren't going anywhere, and you have an empty p orbital. So this is sp2 hybridized at the moment with an empty p orbital. And you've got a little bit of electron density in the p orbital from this side that's actually property of the bromine and is going that way, and you've got a little bit of electron density on this side of the p orbital that's property of the sulfur, but it's coming in. And these two processes are happening simultaneously. So the sulfur's coming in and causing the bromine to leave. And by the way, it could go in reverse, right? The bromine could come in this way and cause the sulfur to leave. But anyhow, the transition state is that point in the middle. And in the middle, what you see is that this is now perfectly flat. But if you go to this direction, if the sulfur comes in and kicks the bromine out, then it has to be coming in from the backside of the bromine. And vice versa. If the bromine attacks, then it has to come in from the backside of the sulfur. And so that's why the stereochemistry inverts, going from bromine forward to sulfur back. And if we were to run this reaction in reverse, naturally the bromine would have to attack from the backside of the sulfur and end up in front. The key thing to recognize in this particular transition state is that you have a substantial amount of delta minus on the sulfur, which was minus to begin with, and a substantial amount of delta minus on the bromine, which is leaving and ends up as Br minus. But in the meantime, on the carbon itself, you have a substantial amount of delta plus. And so there's a large amount of charge involved here. Most of the minus is on the sulfur and the bromine, and very little electron density is around the carbon right now, so that's why that's plus. But this is coming in and forcing that to leave, and this is the key thing that's happening in any kind of SN2-like reaction. The sulfur comes in and causes the bromine to leave, but these two processes happen simultaneously, which means that the sulfur needs to come in from the backside of the bromine and cause the stereochemistry to invert.